So if the correlation is 0.9 and it is positive, we say the correlation is they are highly correlated with each other. So if one goes up, the other should also go up. If it is negative, then if one goes down, the other goes down. And it is linear correlation. It does not tell you anything about the nonlinear relationship between them. The exact same thing about a time series, but it is called autocorrelation because the correlation is not with any other independent variable, but rather it is with itself. And what I mean by that is if you look at this bottom line chart over here, I have these two purple dots. And these purple dots, it is possible that maybe this one purple dot over here that's up ahead, let me highlight that. So this might be influenced by this point. In machine learning, we do not see anything like this. We might have some correlation, but it is not in that structured way. So every single point on your time series is dependent in one way or other, or rather it could be dependent one way or other on its past, what has happened in the past. And that's really the distinguishing factor between a typical machine learning model and a time series model. Fixed intervals, so in a machine learning model, we may have data that was captured on an infrequent basis. So let's say we are doing the house prices regression model, right? We could be capturing that data. It doesn't have to be every single month or every single week. We just get the data whenever it is sold, the house is sold, and there is no set frequency to it. Repeated and observable patterns. So in time series, the classical time series, we assume that everything is repeatable, and we capitalize on that, and the classical time series forecasting models capitalize on that and try to extract that pattern as much as it can to predict the future. And the last is the black box versus the white gray box. So many of the machine learning models, neural networks and random forests and a lot of the tree-based algorithms, in some way or other, they are very black box. You feed something in, you get something out, but there is no statistical backing to it. You get it, the accuracy could be high, but you might struggle with actually explaining what's going on. And that is where classical time series forecasting method stand out. And you will see that, what I mean by that. Now, when I say classical forecasting methods, we've seen in the labs where we do the bike sharing example and we apply regression analysis to it. That is, so regression, if we do linear regression, that is a statistical method. But the classical forecasting methods are very different from that. The exponential smoothing method or the SARIMA that we will be discussing, all these are classical forecasting methods. I'm not going to go into applications, but I think that those are pretty self-evident. So why study these classical methods? We have seen time and again, you just apply XGBoost to anything and then you get superior results. You pretty much don't even need to consider anything and you'll get the results. Well, that's not always the case. And in case of time series especially, those methods, those black box methods don't quite really work very well. So M3, just like Kaggle, M3 is a competition for time series forecasters, and it's not held every year, but in an M3 competition, they give actually thousands of different time series of various granularities and applications. So you will see weekly data, daily data, monthly, quarterly, bi-monthly, bi-quarterly, and for various applications as well. So for business application or econometrics or healthcare and lots of other applications. And the goal is, can you apply your forecasting model to all of those and then see which one stands out? And if you see in this chart over here on the y-axis is the error metric. I think it is RMSE. I could be wrong, but the lower the better. So if you see the statistical methods stand out, and by wide margin. So ETS, we will be discussing that in depth. But ETS, ARIMA, DAMP, all of these are statistical methods, and they perform far better than any of the machine learning models. So if you see on the far right over here, we have cards, that's the decision tree. We have support vector regression. RBF is your kernelized Bayesian function, KNN, LSTM, neural networks. So all of these, they fall apart. These methods fall apart when it comes to machine learning models. And that's not, I mean, that's not the general case. It may turn out that in your particular application, maybe the machine learning model works far better than the statistical methods. But if you are given a time series, then if you're given a time series, then you should always start with a statistical method and then go from there. This will also help you doing this, applying statistical methods first, will also actually help you identify critical features and do some feature engineering, which will help you in your machine learning models. By the way, you can go to this paper over here. I provided the link. It's an excellent paper that describes what their findings are from the M3 competition. The M5 competition actually just ended a couple of months ago. And in that case, light GBM, so gradient boosting regressor, actually won that competition. And we'll discuss that as well. Why is that the case? So classical time series forecasting. There are a few items that or things that concepts that we need to understand. The stochastic process view, then temporal structure of the understanding and describing the temporal structure of the time series. So what is the stochastic process? So stochastic, if you're not familiar with the term, that just means probabilistic. In case of a time series, what we are seeing is stochastic versus deterministic. Deterministic meaning if I specify time, you'll get the exact same output every single time. So just a y is equal to mx plus b, or your output is maybe just a sine function. So every single time you're going to get the exact same output. That is deterministic. Stochastic, on the other hand, has some probability density associated with it. So assume, for example, in my case, I am a mechanical engineer and we make parts in our factory. And there is a process that produces these parts, right? And there is a pattern associated with the production of those parts, meaning I can say that maybe on an average we make 35 units per hour with some probability associated with it. If it is a normal distribution with a standard deviation of let's say 5, then there is a 68% probability that it's going to fall between 35 plus or minus 1 sigma standard deviation. So there is some probability associated with it. If we look at this chart over here, this is my time series. If I take any single point here, this could have been any other point but that. There is some probability associated with that point. It just happens because of the random nature of the process that it happened to be that point. But it could have been any single point on this curve, the distribution on this curve. It is more likely to be, it's more likely to be this point because that happens to be the mean, and less likely to be a point that's in the tail end. So that's what the stochastic nature of it. Meaning, if we were to do this process again, maybe it could have been over here, or it could have been maybe somewhere over here. Chances are maybe not. So based on the based on the probability uh, associated with it, we may have some different outcome of that time series. And how that applies to your forecasting is when we do the forecast, we are actually forecasting a bunch of different futures. So we are capturing these distributions for each time in the series. So if I'm forecasting 3 time units into the future, I'll have a distribution associated with this, a distribution associated with this, distribution associated with this. And then when we say, well, next quarter, our forecast is going to be 80 units, we are saying that's 80 mean, so that's a point estimate. And that's a really, really important point to keep in mind when you are doing forecasting, that there is a mean estimate. You're saying there is some forecast, but there is always some uncertainty associated with it. There's always some probability associated with it, and that is captured by the probability distribution around it. So when somebody says, well, the forecast is going to be something, your next question to them should be, okay, what is your confidence with that, or what is the error associated with that error estimate? Because remember again, the forecast always has uncertainty around it. And the reason is like, the reason for that is when you're doing forecasting, you have 2 primary goals: to make accurate forecasts, so that would be the point forecast, the mean forecast, and there is also this uncertainty around it. So this confidence interval, the shaded confidence interval around here, that's the uncertainty around it. So if you create a forecast in R or Python, you'll see this blue called cone of uncertainty. Can somebody please confirm they can see my screen? Because Suresh says it looks like on his end he sees that the screen is stuck.
I think we can see your screen. Is just that the points what you are trying to point, we cannot see that. So that's why I think that
Okay.
was the comment. Yeah.
Oh, I see. Okay, got it. Okay, so that's the forecast associated with it. So when you create these forecasts in Python or R, you'll always see, and you always want to show these forecasts to your stakeholders, what the uncertainty around those are. And if you ask me, based on my experience, uncertainty is far more important to capture than the mean forecast. So mean forecast is good, but uncertainty is even more important. And I'll take an example. So the 35 units that I said earlier, if I go to my manager or my supply chain people and say, forecast next quarter is going to be 35 units, that's good. That's helpful to know. Something is better than nothing. But if I tell them the uncertainty around, based on what we have, what we know, is 20 units to 75 units. So that's quite a wide range. That helps them with the planning process, that the demand could be as low as 20 and it could go as high up as 70. So how do we plan our resources? How do we make sure that we can mitigate those risks that might arise because of that uncertainty? So that's why uncertainty is extremely important to capture. And sometimes you may want to do both. You want to capture both the forecast and then the uncertainty. So decomposition of the time series. What we do with time series is we decompose it. We break it down into 3 main pieces: the trend of the time series, cycle, and then seasonality. So this curve, this pinkish red curve, is the trend. You describe trend as just it is going up or going down. So it is increasing or decreasing, and it spans the entire width of your time series. Seasonality, on the other hand, it is fluctuating and it is short term. So if you are an ice cream, if you have an ice cream shop, you're likely to see the sales jump up maybe on weekends and maybe only in summer, but not so much in winter. So that's the seasonality associated with it. You may see the seasonality, and we'll see that in a minute, but seasonality just describes in your natural time period, is there a repeatable pattern when your time series goes up, down, and is that repeatable? And how frequent it is. Cycle, on the other hand, is much more long term. So cycles appear, so we have fluctuations in cycles as well, but cycles appear on length scale of 10, 15, 20, 100 years. So the COVID-19 situation that we are in right now, that would be an example of a cycle, or a recession that might happen in the economy. That's an example of a cycle that it will affect your time series, but over a long period of time, it will just be a small blip. There's not much you can. There are ways to capture that as well, the cycles. But for business applications purposes, we're not so much. We don't model that as much. And then there is an error term, again, the irreducibility, irreducible error, that's just the nature of the mathematical modeling of it. That's just the error associated with it. I will be sharing the presentation later, Jude. So yes. Trend and seasonality. Further, you classify trend as damped or undamped. So undamped trend would be it just keeps going up, and it looks like if at any point if you were to cut it down, yeah, it's just going to keep going. That's unlikely scenario. Maybe if you are a small shop and you're trying to sell something, then in the initial years, yeah, maybe sales just keep going up. But if you are a mature business with a legacy product, then probably not. You will see an upward trend, but the trend might be slowing down. That's where the undamped trend comes in. Additive, the seasonality can further be described as additive versus multiplicative. And the difference between the two is, if you see the dotted line in this blue shaded area, if I were to say, we compare that's compared to this average dotted line. If you can describe your in your time series such that, well, my sales are compared to my average for the year, if my sales will go up by 1,000 ice cream cones in December, and then it will go up again by 1,200 units in January, but will go down by 800 units in general. So if you can describe it in terms of single units, then that's an additive seasonality. However, if you have something that you describe in terms of multiplications, or in terms of percentages, that it will go up 10%, 15% every single year compared to your base level, then that's a multiplicative seasonality. In general, you will see that in real life, it falls in somewhere in between the two. It will be additive, a mixture of additive and multiplicative. You can convert your multiplicative into additive by just taking the log of it, because a log of a multiplication is just summation. So you can convert your multiple seasonality into an additive if you just take the log. So that's that. I've added a reference here at the bottom. Let me paste that into the chat window. And let me go over here. So this, I can't pronounce his name, but here is a time series forecasting researcher. You should definitely check out his blog. But on his, it's very hard to distinguish basically between if it is a additive or multiplicative seasonality. So here is a quick way So is this a additive or multiplicative? Based on this, I think it looks like additive, so I'm going to say additive. I don't know the answer, by the way. But if you go over here and then if you do 10 of these, you will see that it is actually quite hard unless it is quite evident from the graph or plot, but it's actually quite difficult to figure out if it is additive or multiplicative. So Maureen, I see your question. Let me answer that one more time. So Maureen is asking, can you explain additive and multiplicative one more time? So look at this red line. And if you draw a vertical line from the top to the bottom of this red line, you'll see that it stays constant no matter which year you are in. Whereas if you look at the multiplicative, if you draw a vertical line from that red line to this black dot, you will see it is growing in multiples. And there is a way, I show that in my blog, as to figure out whether it is additive or multiplicative. In general, in practice, you apply both additive and multiplicative and see which one works. So.
Sorry, my question was more about the trend, undamped versus damped.
Oh, okay. So damped trend is damped trend if it looks like that your time series just keeps going up, and if it is not slowing down, so it's basically the momentum or the rate of change of your trend. If it keeps going up without slowing down, so if you were to take slopes at various intervals, if the slope is always increasing, then that is an undamped trend. Whereas if it looks like it is slowing down, if you were to take slope at various points, then damped is what you want to do. Now, again, based on my experience, damped, that is evident, right? So if I were to draw a vertical line here and then check for this time equal to t, what is the forecast? Undamped is going to give me a significantly higher number than damped. In practice, we want to use damped because we just want to be a more conservative. Damped usually works out to be better. Again, you'll model that and you'll figure out, I try to identify whether it is damped or undamped. But in practice, damped with combination of another time series forecasting method usually works quite well. Stationary versus non-stationary time series. Stationary time series is if you look at this first example in blue, if you were to calculate the mean, and if the mean stays constant over the length of the time series, it does not change at all, and the variance of it stays the same, then it's a stationary time series. If the time series is stationary, if you think about it, that's an easy problem to solve because the mean, that's not going to change at all. The variance, that's not going to change. So you just have to figure out what probability distribution it comes from, and there you have it. That's your forecast. So for a stationary time series, it's always the mean stays the constant over the length of your time series, and the variation, meaning how it goes up and down relative to that mean, stays constant. On the other hand, if either the mean or the variance or both change over a period of time, then that's a non-stationary time series. So the middle example here, the mean and the variance both are changing. It's going up and down, and that's how most time series work, right? So this is the most common thing. And then in the last case, you have the same mean. So the mean is not changing because the fluctuations are symmetric around the mean. So it goes up, goes down, but by the same amount. So it cancels out, the variation cancels out. And so the mean is constant, but variance is not. The implication of this, why we want to identify this, is because, as I said earlier, if it is stationary, the problem solved, we don't even have to do anything. If it is non-stationary, then the classical methods that you are going to use are going to be different. And this might be your first indication as to which time series method to use, whether you should be using maybe machine learning model or a classical time series model. The SARIMA or the seasonal autoregressive integrated moving average model that expects the time series to be stationary. It needs the time. You cannot have a trend in your model. It expects your time series to be stationary. So you cannot apply SARIMA to that, but ETS or exponential smoothing models can be applied to both stationary and non-stationary. How do we know, other than visual observation, how do we know if it is stationary or non-stationary? Well, you can apply what's called as a decupuller test, and it's pretty easy. Both in Python and R, decupuller test, you just pass your time series and it spits out your significance value, p-value, and if it is less than the significance, then yes, that's a stationary. Or you can create ACF plots, and we'll talk about this in detail. So if there is one thing that you want to take out from my presentation is this ACF plot, because I struggled quite a bit in understanding these ACF plots, and this will help you a lot in your machine learning models when you try to do your machine learning model. So stay tuned for that. Another quick way to make the series stationary is by differencing. And by differencing, what I mean is, if you were to just take, let me go to the next slide and maybe I'll explain that. If you have this time series over here in the box here, what you're going to do is you just take a difference from the value that's previous to the next value. So I will take 58 minus 286, 58 minus 348, 40 minus 348. So we're taking lag, or we're just going back. It doesn't have to be one back, but it just turns out that when you do that, you detrend the series. You can also detrend the series by if you were to take mean of this, average of this time series, and subtract that from every single observation, then it's a mean differencing, and your series becomes stationary. Try it out, and you will see. You may have to do that a couple of times or 3 times to make the time series stationary, but that does work. Autocorrelation is the next property. So let me go back here. So these are the things that we talked about so far. Stochastic process. So time series is a stochastic process. There are 3 components associated with the time series. You describe the trend and the seasonality of the time series, and whether it is damp, undamp, additive, or multiplicative, whether it is stationary or non-stationary. So we already have found a lot of terms to describe how the behavior of a time series. Next one is the autocorrelation, and we talked about this earlier a little bit. But as I said earlier, the autocorrelation is the correlation of the time series with itself. So what it's going to do is, go here. I just created some random numbers. Let me blow this up a little bit. I just created these random numbers. We take the first lag meaning we shift the time series down by 1 time unit. So it goes to 286, and we stop at here. Do the same thing over here, and then the third lag. And all we do is, I'm going to take correl of
we are just seeing your presentation.
Oh, you are? Okay, let me stop and presenting, and then see if I can see if Excel. Let me know when you can see it.
Got it.
Got it? Okay, perfect. Thank you. So let me back up again. So I'm going to take this time series. I'm going to shift it by 1 time unit. Then I'm going to shift it again by 2 time units. So these 2 are blanks, and shift it again by 3 time units. And then to find out if this series is correlated with its past, I am going to take a correlation of this, so the time series itself with its first lag. So minus 1.74. So this time series at lag 1 is negatively correlated with itself, and it is rather low correlation. That's just because I created random numbers, but you may have something else. I'm going to stop presenting here and present my screen. Okay, so we do that for various different lags and try to identify how is this time series correlated with itself. And the importance of that is because it tells us, can we actually use this time series? Is there information in this time series that we can extract from the past to predict the future? If there is none, then there is no point in going through this exercise, and there is not much we can do about it. Now, if you think about it, this is exactly what we did in our bike share example in the program. We took, I believe we went like every hour or maybe every day, I forgot, but I think every hour, and we went back and calculated the lag, extracted what was the demand every hour for the past 12 hours or something. So this is exactly what we did. And the reason why we had to do that in machine learning model is because machine learning model cannot extract that information without you specifying what that autocorrelation is. So if you understand autocorrelation, you can use this in your machine learning model, because in that example, we extracted 7 lags, right? But who knows, that whether we should be using 7 lags or 14 lags, or maybe multiples of that. And the way you find that out is based on the autocorrelation plot. So what the autocorrelation plot does is you calculate this matrix is nothing but 1 is autocorrelation with itself, 0.8 is autocorrelation with its first lag, second lag, third lag, and it's going to be symmetric. And if I flip this around, this is what your autocorrelation plot is going to look like. So at my first lag or 0th lag, which is with itself, autocorrelation is 1 because it's just itself. At 1, it's going to be 0.8. At 2, it's 0.4, and then at 3.2, and so on and so forth. And we will look at the significance of this, but it helps us define the temporal structure of the time series. If the autocorrelation is low or very small based on a critical value, then the time series is just stationary, right? Because there is nothing to extract from it, it's just stationary time series. But the way we read the autocorrelation plot is based on the strength. That is, if it is positive, how much positive, or what is the strength, meaning the magnitude, whether it's 0.8 or 0.4. So that tells me lag at 1 is significant compared to lag at 2. The direction, whether it is positive or negative, the trend, meaning how fast it is going up or going, is it increasing or decreasing? So trend, basically the same thing. Yeah, increasing or decreasing. So let me give you some examples of that. Let's go over here. So if the autocorrelation, okay, let's shift it over here. So if the autocorrelation, if you look at the autocorrelation plot, and if it is gradually going down, then that is an indication of trend in your model. So that's number 1. So you want to look at how what is the slope of that autocorrelation plot. So that's number 1. Number 2 is it changing sign or no? If it is changing signs, then that means that you have an alternating time series. So it is, and it's also an indication of mean reversing process, meaning it is going to go up, but it's also going to go down at a certain fixed time interval. You also want to notice where does the strength, at what time interval does the strength go up or go down. So in this example, if you see it goes up at 6, so after 5, then this is 6, then it goes up at 12, and then 18. So that is an indication that this time series has a seasonality of 6. So this is a, I don't know what 6 is in this case, but let's just say this is the 6 months or semi-annual time series. So your seasonality is 6. So now we know that we can define the time series as whether it has seasonality or not. If the time series has both trend and seasonality, then it's going to be a mixture of these two. It's going to go up and down, and then it's also going to gradually increase or decrease. So if you notice, it's slightly going down here because of the trend, but it's also alternating, indicating that we have seasonality in this case. So now let me back up again. So far we have understood that when you get a time series, you want to identify whether it is stationary or non-stationary, whether it has trend or seasonality. If you plot the autocorrelation and you identify whether it has trend or no trend, whether there is a seasonality or no seasonality, what is the seasonality pattern. If you see multiple peaks in your ACF plot, then that means you have multiple seasonalities present. So let's take an example of a time series that is weekly. So you're capturing some sales data weekly, and you might see peaks that are based on, let's say, every week, every 4 weeks, and then maybe at the end of the month peak and at the end of the quarter peak. So things like that. So the more granular your data becomes, or more granular your time series becomes, the more peaks that you're going to have in your ACF plot, and that indicates multiple seasonalities in your time series. The implication of that is if you have multiple seasonalities present in your time series, the classical methods do not work very well. The classical methods work when you have fixed frequency or seasonality. So weekly, bi-weekly, quarterly, monthly, yearly, that. If you go any lower than weekly, for example, let's say daily frequency or hourly or sub-hourly time frequency, then in that case you tend to have multiple seasonalities in your model, and that's where classical time series forecasting methods do not quite work very well. There are ways to get around that, and you can deal with it, but right out of the box, you cannot deal with those. So again, doing an analysis like this will give you also an indication as to whether you should be using classical or whether you should be using a machine learning model. And based on these peaks and identify how these peaks are correlated with each other, it will also tell you what features you can, what kind of feature engineering you should be doing in your model. If you look at this ACF plot one more time, another way to explain this is the first 6 months, it is negative, and after that, after next 6 months, after that is positive. So the way you can describe, if this were to this was a sales forecast or a sales time series for a sales, then you would say that the way you would describe this is our sales tend to go up, and then the following quarter they tend to go down. So that again gives you an intuitive understanding of understanding the behavior, the temporal structure, and the behavior of your time series that you can actually explain to somebody. Which you cannot really do easily with your machine learning model. So also helps us to identify the MA and let's not get into that at this point, but let's move on. Splitting the data, that's another distinguishing factor between ML and classical methods. In machine learning, we just shuffle the data and randomly split it into train and test. But in case of time series, because of this autocorrelation, we should be using continuous data and then just split it based on the time. So because the goal is to predict in the future, we just use the most recent time series data, at most recent time series as your test. You can also do cross validation in this case, and that would just be we just slide going forward. But that's really the main difference between the two. And in case of time series, the way you want to so in machine learning we do 80-20 split. In time series, the way we do it is first we identify what is your forecast horizon. So the forecast horizon in this case is, let us say, I want to predict 4 quarters into the future. Then you hold out 4 plus some amount, so maybe 6 quarters, and then the rest of the balance is your training data. So the steps for the EDA are split the data, plot the data. If there are any missing values, we can no longer use just mean imputation. We'll have to use maybe averaging or forward fill, meaning you just use the last value, or backward fill, that you just use the next value. That is the distribution symmetric or non-symmetric. It doesn't have to be symmetric, but if it is non-symmetric, then you would apply some transformation to it. Are there any outliers? The implication here is classical time forecasting methods are not extremely robust to your outliers. Also, the error metric you want to use, if there are any outliers, then you would use you would not use RMSE. You would rather use MAE or MAPE, whether it is stationary or non-stationary, whether it is additive or multiplicative, seasonality is fixed or non-fixed, trend is damp or undamped, exogenous variables, meaning do you have any other variable that might explain your time series more? So if in case of your ice cream data or the ice cream sales, you might want to include maybe the holidays, for example, or you might want to include the temperature in your data. ETS, exponential time series, does not capture that very much, whereas your machine learning models would. And whether it is intermittent or continuous. If it is continuous, then you can use machine learning models. If it is intermittent, meaning let's say you're an antique retailer, then you may have sales, this month, you may not have any sales for 3 months, and then again you have a big sales maybe 6 months from now. If the time series is intermittent, then that's going to be really challenging. So the goal of all of this is you want to explain your behavior of your time series, whether you're using machine learning or classical methods, in some terms, in your own words. And the reason for doing that is because when you get your new data, you can see if it fits that description or not. If it does, then good, your time series model is still good. If it does not, then you'll have to retrain it. And second, when you do the forecast, can it fit that description? Can it fit that narrative that you have built based on the EDA? And that will also help you identify, other than quantifying the error, this will also help you identify if it is good, if it is a good fit or not. So the question here is, what is exogenous variable? Exogenous is just an independent variable. So in the machine learning model, you have many factors, right? Many independent variables. In time series, we only have one sales data, and then there is some time component associated with it. We don't explicitly model the time component, we just extract it from the data, the methods do. But if you were to include, let's say, temperature data, more independent variable, that would be your time series data. We have 6 minutes left here. My goal was really to explain the EDA process as much as I could. But I was going to show the EDA steps in a Python library, but you can go to my blog. So Pawar, let me type it here, pawarbi.com, and I've shown it over here. So the time that we have left, let me go over an important class of method. If you want to learn one method, that would be this ETS, error trend seasonality exponential smoothing method. So while the time that I have left, let me explain that, at least the conceptual part of it, so you understand how to use it and what it does. So exponential smoothing is, as the name suggests, we smooth out the time series, and the way we do that is we attach some weight, just in linear regression. So in linear regression, we attach some weight, right? We attach some weight to each of the independent variables. In exponential smoothing, we do the exact same thing. We attach some weight to your past data. And let me switch over to my Excel sheet, and I'll show you how. Oops, not this one. Let me try one more time. Oh man, so it's not allowing me to share anymore. Damn it. It's not allowing me to show anymore. Okay, sorry guys, I have trouble over here. I'm no longer able to share, so I don't know what to do. Let me screen. Just give me 1 second. Let me log out and log back in. Hopefully it won't disconnect you, but if it does, please, if you're still interested, then please log back in. Let's see if that works. Sorry about that.
Sandeep, I think you're on mute if you're talking right now.
Oops, sorry. Thanks for sticking around. It won't let me share my Excel sheet. Let me try just one last time. If it does not work, then I'll just explain using, yeah, let's just stick with this. Okay, so what exponential smoothing does is we have this time series, 286, 58, 348. We are going to attach some weight to it. So let's say the weight we are going to attach is maybe 70%. So we want to capture 70%, attach 70%. So take 70% of 286. Then maybe the next weight is 20%. So 20% of 58. Next weight after that is 6%, so 6% of 348, so on and so forth. And the reason why it's called exponential smoothing is because, so back here, exponential smoothing is because of this term over here. If you, and I was just going to show that in Excel, but if you were to get an alpha value of 0.7 and just keep increasing or going down and increase this exponent over here, you'll see that the weight dies down significantly after, let's say, maybe fifth or sixth observation. So you can think about alpha value as nothing but a percentage that you want to attach to your observation. And that's all it is. There is nothing more to it. The higher the weight, the more weightage we are giving to our most recent observation. If the alpha value is low, then you are giving higher weightage to your more past observation than the recent observation. And the way we find out alpha value, we don't have to. The Python and R does for us, but the way it finds out alpha value is exactly like what we do in regression, just by calculating, minimizing the SSE, and yeah, that's all it does. Now, what the exponential smoothing does is, remember the trend and the seasonality that we find out? It decomposes the time series into trend and seasonality, and then attaches these weights, these exponential weights, to each of those factors. So L is here your level, meaning the average. B term is, and the beta is your trend, and S is your seasonality. So it is going to decompose your time series and then attach these weights to each of these. And then depending on whether it is additive or multiplicative, it will calculate it differently. And let me actually go here. Depending on whether you're using damped or undamped, whether you're using additive or multiplicative seasonality, you will get different, it will capture different dynamics of your time series. So if there is no seasonality, straight line. If it is a multiplicative seasonality with additive seasonality with multiplicative trend, it's just going to keep going up, and then it's going to fluctuate with some fixed amount, so on and so forth. So the way you describe a time series exponential ETS model is with AAA. A is your error term. Second A is your whether it is additive or damped, and then after that is your seasonality, where there is no seasonality, additive seasonality, or multiplicative seasonality. Reason for understanding this ETS type of a model is because if you go back, look at the first model or the method that beat all the other methods, ETS. It works really well if you have weekly, monthly, quarterly, yearly data. ETS will almost always beat your any other model. So, and this is available in Excel too. So if in Excel, if you do the forecasting, it's actually doing the AAA. It will assume that you have additive seasonality, and it will do the additive seasonality for you. In Python, you can only do additive and additive damped. But as I mentioned earlier, if you have multiplicative component in your time series, then you just apply log to it and it becomes additive. So that's not a big deal really. You can just apply that and it will work that way. So the modeling steps in time series are you do the trend test split, do the EDA as I described earlier. You do the transformation if required for variance stabilization or for converting your multiplicative into additive. Do the forecast, do the valuation either using RMSE or MAPE. RMSE, you usually use RMSE, you never use R squared error for time series analysis. But RMSE is the RMSE that you use in your regression. MAPE is just the percentage. So if you take your actual data minus your forecast and divide by your actual, you'll get MAPE. And the last is AIC, AIC is a Geikie information criterion that uses maximum likelihood and for choosing a model, you want to use RMSE or rather AIC because it penalizes overfitting. So the lower the AIC value, the better it is. Just a caution with AIC is that you cannot compare AIC from ETS to AIC with, let's say, Sarima model. But AIC has to be applied to the exact same class of models. And yeah, and the most important part after that is residual check. You want to plot the residuals. And if the residuals are stationary, you already know what residual stationary is. You already know what stationary is. But if the residuals are not stationary, then that indicates you have not extracted all the information out of that time series. There is still something left that needs to be captured. And the way you would capture more that is either you stabilize or you take a square of it, or maybe you need to add an exogenous variable, something along those lines. If the residual has non-zero mean, then that indicates your forecast is biased, and that's an easy thing to fix because let's say your forecast, you fitted the model and you calculated the mean of your forecast, mean of your residuals, and that residual mean is, let's say, 10 units. Then you just add that 10 units back to your forecast and you got rid of your bias. So it's an easy thing to do. So the important part always after fitting your model is to look for if the residual is stationary or not. So that is far more important than anything else. And if your variance is constant or not, that is more applicable to identifying if for the uncertainty rather than identifying the accuracy of your model. Okay, so I don't think we have time for Serimax here, but for method selection, you would go down by looking at the time series. Let me actually go back. There are still quite a few people on the call here. So let me explain Serimax in a little bit, and just stick around if you want to listen more. But so Serimax is seasonal autoregressive integrated moving average exogenous method. It's quite a mouthful, but it's actually very simple. Seasonal meaning you have some seasonal component. Autoregressive is you look at your past data and it's just a regression. So yeah, it's just a regression. So remember we looked at here, right? So we took 286, first lag, attach some weight to it or coefficient to it. Take the second lag, attach some coefficient to it. Take the third lag, attach some coefficient to it, and that becomes your autoregressive model. Okay. Moving average model, on the other hand, and it has a component P. P meaning your order of your partial autocorrelation. Moving average is weighted average of the past errors, meaning we describe it in terms of weighted average of if you were to do a forecast, you do a forecast, predicted minus the forecast, whatever is the error, you attach some weight to each of the errors in the past, and then you just calculate your emitter. And to identifying these terms, P, D, Q, P, D, Q, P is your order of your order for your autoregressive part. D is differencing. Differencing meaning with the differencing that I talked about earlier, that if you difference your previous value, you stabilize the time series, and that's what the D does. Because for Sarima model, you need the time series to be stationary, so you are differencing. And then Q is order of the Q, that's based on identifying in your ACF. Now, auto ARIMA in R, and then PMD ARIMA in Python does all that for you. You don't really have to worry about it. I wish I had more time to explain how to identify this P and Q value and D value looking at the ACF, PACF plot. But just keep in mind in general is that M8 is not, so AR is more common than M8. So it is more likely that you have AR autoregressive time series than moving average time series. And yeah, and that's all it does. You fit the Serimax model, and then and you get your result. So the way your method selection is going to work is you start from the top, go down, and identify whether it is stationary, non-stationary, whether you have damped or undamped, which lags are significant. If it is, do you need exogenous variable or do you not need exogenous variable? If you have high granularity or low granularity. Granularity meaning whether it's a hourly data, daily data, or is it a higher, less granularity like yearly or quarterly, bi-monthly, like that. So based on that, you would choose your model and then fit your model and get your predictions. Well, that's about it. Maybe we can do another session and I can keep talking about this. But if you have any questions, feel free to let me know in the Slack channel, and I'll be happy to answer. I really appreciate you sticking around and being present here for my presentation. Appreciate it. Thank you very much.
This was really good. Thank you.
Thank you.
Thank you.
Thank you.
Thank you, Sandeep.
Thank you.
Thanks, Sandeep. Thank you very much.
Thank you, Jude. Appreciate it.
Thank you, Sandeep.
Thank you.